Hi, welcome to educator.com. Today we're going to talk about t-distributions. So previously we learned that there are different situations where you use z and when you use t. And today we're going to talk about when to use z versus t. And then we're going to also break down and sort of reflect and recognize what is z and t, what do they have in common, and what's different about them. And for certain cases, we're going to ask the question, why not z? Why t instead? What doesn't z have? What's sort of deficient about z? And then we're going to talk about rules of t-distributions. They follow certain patterns. And t-distributions are a family of distributions separated by degrees of freedom. So different t-distributions have different degrees of freedom. So we're going to talk about what is degrees of freedom. And then we're going to talk about how degrees of freedom relates to that family of t-distributions. And then finally, summarize how to find t. Okay, so first off, when do we use z versus t? And we sort of covered it in previous sections where we looked at whether we knew the population parameters or not. In hypothesis testing, we frequently don't know the mu of the population, but sometimes we are given sigma, right, for some reason or another. And in this case, we use z in order to figure out how many standard errors away from the mean we are in our SDOM. But in other situations, we do not know what sigma is. And in that case, we use t in order to figure out how many standard errors away our x bar is from our mu. And just to draw that picture for you, remember, we're always interested in the SDOM because the SDOM tends to be normal given certain conditions. And although mu sub x bar equals mu, right, given the central limit theorem, what we often want to know is if we have an x bar that falls here, or an x bar that falls here, or a x bar that falls somewhere like here. We want to know how far away it is from the mu sub x bar. And in order to find that, we wouldn't just use the raw score and just get the raw distance, but we would want that distance in terms of standard deviation. But because this is the SDOM, we call that the standard error. So we would either want a z or a t. And these numbers tell us how many standard errors away we are from this point right in the middle, the mu. Okay, so what is z and t? Well, the commonality as we saw before, is it tells us the number of standard error away from mu sub x bar, right? And that's common to both. Right? And that's what the z and t score both have in common. And because of that, their formulas look very much the same. For instance, one way we could write the z formula is like this. Let me just write it here, let's see. So z equals we have x bar minus mu, right, or mu sub x bar, they're the same. And this gives us the distance in terms of just the raw values, right? So just how many, whatever, inches away, points away, whatever it is, whatever your raw score means, degrees away, right, divided by standard error. Right? But if we sort of double click on that standard error and look at what's inside, then this standard error, also written as sigma sub x bar, because it's the standard deviation of a whole bunch of means, is equal to sigma divided by the square root of n. Right? Now, if we look at the t-score formula, then we have almost the same formula, at least at first, right? We have that distance divided by how big your little steps are, how big your standard deviations are. But when we double click on this standard error, right, like something on a desktop, you double click it and open it up. What's inside? Well, you could also write this one as s, little s sub x bar. And that would be little s divided by the square root of n. And herein lies this difference right there. That's our difference. So here the difference is that standard error found using sigma, the true population standard deviation. And obviously, if you use the real deal, that's sort of better or more accurate. Then the standard error found using estimated population standard deviation, right? And that is S, right? And S is really estimated from the sample. And if we double clicked on S, it would look like this. It's that basic idea of all the squared deviations away from X bar, right? Away from the mean of the sample. So X sub I minus X bar, right? Squared. We have all these squared deviations and we add them up, right? Divided by not n, but n minus 1, because this is our estimate of the population standard deviation. And then all of that under the square root sign in order to just leave us with standard deviation rather than variance, right? And so this is an estimate of population standard deviation. It isn't the real deal, so it's not as accurate. So one thing you should know is that the z-score is less variable, and the t-score is going to be more variable. And that's going to come into bear on why we use which one. Okay, so why not z, right? When we have situations where we don't have the population standard deviation, why not z? Why can't we just be like, so you're using S, let's just use z anyway. Why can't we do that? Why be a stickler? Why do we have to use t? Well, it's because we use S. This is actually something a little bit weird. The weirdness comes from the fact that this S is much more variable than sigma. Sometimes when we get our estimate is spot on. But sometimes when we get our estimate is off, right? And that's what we mean by it's more variable. It's not going to hit the nail on the head every single time. It's going to vary in its accuracy. Now, z-scores are normally distributed when S-DOM is normal. And here's sort of what this means. The way you could think about it is like this. When the S-DOM is normal, and we pick a bunch of points out and find the standard error from those points and plot those, we will get another normal distribution. But that's not necessarily the case for S, okay? So here we need to know that z-scores are nice because z-scores are always going to give you it's going to perfectly cut up that normal distribution accurately for you. Because remember, the normal distribution, it always has that probability underneath the curve, and it has these little, marks, right? And these can be said in terms of z-scores, right? And what's nice about the S-DOM when it's normal is that when we have the z-score, it'll perfectly match to the proportion of the curve that it covers, right? So this will always match, right? The problem is t-scores don't match up in this way. And so we can't just say, well, why don't we just call it a z-score a t-score and then still use the same areas underneath the curve? Well, we can't do that. That's just a superficial change, right? Okay. And so here's what we mean by the z-scores are normally distributed. When you get z-scores and when we talk about normal distribution, I'm not just talking about that bell-shaped curve. Yes, overall it should have that bell-shaped general shape, right? But it's a little more specific than that. You could have the bell shape and have the perfect normal distribution. For instance, 1 standard deviation away will give you 30, this area will give you 34% of the area underneath the curve. This area is about 14% or 13.5%, and this area is about 2%, right? So that is a true normal distribution. Now this, on the other hand, it looks on the surface as if it's normally distributed. It looks like that bell-shaped curve, but it's not. Here's why. This area, it doesn't actually, so I should have actually drawn it a little bit differently, but I wanted to show you that don't go by appearances, appearances can be deceiving. So this might actually be a little bit less than 34%. It might be something like 25%, right? And so if that was the case, you would see this area, right? And that area is not 34%, it's 25%. Not only that, but this area is now a little bit more than 13.5, it's around 14%. And now this area is not 2%, it's 11%, right? So although it looks like a bell-shaped curve, it's not quite a normal distribution because it doesn't follow that empirical rule that we had talked about from before. Now what's nice about z-scores is that z-scores will always fall in this pattern. These z-scores will always correspond to these numbers. So that's why you could always use that z-table in the back and rely on it. But t-scores are not going to do that for you. T-scores may not give you that perfect 34, 13.5, 2% sort of distribution. Even though the S-stom might be normal, the t-scores are not necessarily normal, right? So we have a different, we have this normal thing, and then we have t-scores, and it's like, how do we go from t-scores to finding this area underneath this curve, right? That's the problem we have here. Well, it turns out that if n is really, really, really big, then this doesn't matter as much. If n is really large, if your sample size is large, then the t-distribution approximates normal. So it goes towards normal. But when n is small, then you have to worry, right? And also when n is in the middle, or when n isn't really big, it's just large, right? So it's like there's all these situations where you have to worry about the t as well as the area underneath the curve. So if the t-scores are not normally distributed, then we can't calculate this area underneath the curve, right? So if we have our lovely S-stom, right, and we know that the S-stom is nice and normal, right, and we have our x bar here, mu sub x bar here, everything's fine and dandy. We have, let's say, an x bar here, and we want to find that distance, and we find the t-score, right? The problem is we can't translate from this directly into this area. That's the problem we run into. So, this may be a duplicate slide, but I'll use it anyway. So here, what we see is this is sort of more like a t-distribution than a z-distribution, right? And I'm just going to call these z-distributions to call them basically the normal distribution, right? The t-distribution is often a little bit smushed. Like, think of having that bell-shaped curve, that perfect normal bell-shaped curve, and sort of squishing the top of it down, right? It makes that shape sort of bow out a little bit, right? It's not as sharply peaked. It's a little bit more fat, right? A little bit more variable, right? And we had said the S is more variable than the sigma, right? And so it makes sense that the T that comes from S is more variable than the Z that comes from sigma, right? Okay, but you might be thinking, oh great, so what are we, stuck? No, we're not stuck. Here's why. A guy named Gossett actually worked out all the T distributions as well. He went and this is like back in the day, so he manually calculated a lot of the T distributions and found tables, made tables of the T distribution that we still use today. He published those tables under the pseudonym The Student. At the time, he was working for Guinness Brewery, and he couldn't publish because they were sort of like, oh, we don't want you giving away our secrets to very dark beer. And so he published under the pseudonym, and because of that, some of your T distributions in the back of your book may be labeled the student's T, to talk about Gossett's T. Now, here's what Gossett found. Gossett found that the T distributions can be reliable too. You could know about them. It's just that you need more information than you need for the Z distribution. For Z distribution, you don't need to know anything. You just need to know Z, and it'll give you the probability. That's it. Life is simple. T distributions are not that simple, but not that complicated either. They have a few more conditions to satisfy, and the biggest condition that you'll have to know is about degrees of freedom. Because for each degree of freedom, so degrees of freedom of 2, degrees of freedom of 3, of 4, of 5, and so on and so forth, there is a slightly different T distribution that goes along with it. Okay, so let's talk about some of the rules that govern T distributions. So the first one you already know. As T distributions get more normal as n gets bigger. And this makes sense if we step back and think about it for a second. Imagine if n equals n, right? If n equals n, then what would your S be, right? If n equals n, if your sample is like the entire population, then S, right, should be much, 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 much closer to the actual population standard deviation, right? So much better than when n is small, right? It's still a little off because the n minus 1 thing, but it's very, very close, right? And that's the closest you could get. And so T distributions are more normal as n gets bigger because S is a better estimate of sigma as n gets bigger, right? And that makes sense, right? The problem all stems from S. It's variability, right? But as S gets better and better and better and less variable and more accurate to the population, then T gets better, right? Because T is based on S, right? So that's why T distributions are more normal as n gets bigger. Now, T distributions are really a family of distributions. It's not just one distribution. It's a whole bunch of them that are alike in some way. And it depends on n. Rather, it depends technically on degrees of freedom. But you could say it depends on n sometimes because degrees of freedom is often n minus 1. Now, there will be other kinds of degrees of freedom. This is the one you need to know for now. But later on, we will distinguish between different kinds of degrees of freedom. That's why degrees of freedom is actually important as a general idea. It's just the number of data points minus 1. So we have we have a family of distributions. They all look sort of alike, right? They're all symmetrical, and they're unimodal, and they have that sort of, bell-like shape, but they're not quite normal. Not all of them, at least. And as n gets bigger, or as degrees of freedom gets bigger, the distribution becomes more and more normal. Okay, so let's step back and talk a little bit about degrees of freedom first. So let's assume there are 3 subjects in one sample, right? So 3 subjects, so n equals 3, right? That's what I have right here. And we know that just by the blind formula, n minus 1 degrees of freedom is 2, right? But what does this mean? Well, here's the thing. Let's assume there are 3 subjects in one sample, and let's say it's some score on a statistics test. And so they could score from 0 to 100. And if I said, oh, pick any 3 scores you want, and that could be those subject scores, right? Then your degrees of freedom would be 3. You are free to choose any 3 scores. You're not limited, right? You're not restricted in any way. But if you figure out any sample statistic, let's say the mean or the variance, right? So if you figure out any sample statistic, then if you randomly picked 2 of those scores, you can no longer just pick the 3rd score freely. You have to pick a particular score because you already used up some of your calculations for the mean, right? So the mean will constrain which 2 scores you could pick. And this logic will become more important later. So let's put some numbers in here, okay? So let's talk about the case when n equals 3 and degrees of freedom equals 3, right? So it'll be like there are 3 subjects, and they could score from 0 to 100. So pick 3 scores, right? I'm totally free. I could pick, 87, 52, right? My last score, I could pick any score I want. I could pick 52 again. I could pick 100. I could pick 0, right? Doesn't matter, right? So I could just pick any score I want. And if I erase one of these other scores, I just put in a different score, right? And it doesn't matter. I'm very free to vary. But let's talk about this, most situations that we have in statistics where we figure out summary statistics. So here we have n equals 3, but degrees of freedom now equal 2. Here's why. The score is the same. Score can go from 0 to 100. But we also found the x-bar, right? We found the x-bar to equal 50, let's say. If we found that the x-bar equals 50, then we can't just pick any score all 3 times. Can we pick any score for the first one? Yeah, I could pick 0, right? Can I pick any score for the second one? Sure, I could pick 100, right? But now that 3rd score, I can't pick any score. If I picked 72, my mean wouldn't be 50, right? If I picked 42, my mean wouldn't be 50. If I picked another 0, my mean wouldn't be 50. That's a problem, right? And because of that, if this is my data set so far, I've been free to vary so far. I freely chose this guy. I freely chose this guy. But this last one, I am locked in. I have to choose 50. That is the only way I could get a mean of 50. And that's what we call degrees of freedom. This logic is going to become more important later on. But for now, what you could think about is because we're deriving other summary statistics from our sample, we're not completely free to vary. We've sort of locked ourselves down. We've pinned ourselves down and sort of built little gates for us at the borders, right? Okay, so now you know degrees of freedom. And we know that as degrees of freedom, or n, goes up, we see more and more normal-like distributions. So I've drawn 3 distributions here for you. And here, you might notice that I've used basically the same picture of a curve for all 3 of these. And so you might think, oh, they have all the same distribution. not true, because you have to take a look at the way that I've shown you the t down here, right? The way that I've labeled this x-axis, or t-axis in this case, is really going to change our interpretation of these curves. Now, remember what the normal distribution says. The normal distribution says one standard deviation to the right, or positive side, one standard deviation to the negative side. That area should be about 68% of your entire curve. Is that true here? Right? Is that true here? No, it's not. This does not look like more than 50% of the curve, right? This looks like, I don't know, maybe 1/3, right? Maybe a little less than 1/3, right? Now this is starting to look more like 68% of the curve, but still maybe not quite 68% of the curve. It still only looks like maybe 50% of the curve, maybe a little more, right? But this, oh, sorry, my picture is a little bit off, but this, imagine that this was shifted in the middle. This would be more like 68% of the curve, so let me draw it out here. So something like this would be more like 68% of the curve, right? And so, right? And so that's how you could see that as your degrees of freedom increases, it becomes more and more normal, right? Even this isn't quite normal. This isn't quite 68%. It's a little bit less, actually. But as the DF gets bigger and bigger and bigger, that area starts to look more and more like the normal distribution. Now, there is another way I could draw these pictures, and I believe in this other way you could see more easily how this is sort of a more variable version. Remember, I'm saying the t-distribution, you know, it's like you're stomping down on the peak of it, right, and smushing it out a little bit. And I believe that if I draw it in a slightly these same pictures in a slightly different way, you'll see why. So in this case, here's what I've done. I've kept the t-axis the same, right? So now it's labeled in the same way. But I've drawn these distributions in a slightly different way. So now this one is a little like wider, this one is less wide, and this one is even less wide, right? So it becomes more narrow, more like the normal distribution, right? So notice that if I drew the line here, right? Here, a little bit after the 1, after 1 standard deviation away, we see very little of that curve on this side, right? So, you know, I don't know, if that's 50%, I don't know, maybe 15%, 10%, right? Something like that. Whereas this might look sort of more roughly equivalent to this, maybe a little bit less, right? So maybe like 20%, right? And then this looks like much more than this, right? So maybe this is like 25 or 30% even compared to this little sliver. And so in that way, you could see, using the same concepts, but drawing the picture in a slightly different way, that that this distribution is much more variable. Its spread is very, very wide, whereas this distribution is much less variable. And remember, T is all because of the variability found in S. When S is very, very variable, when n is very small, S is very, very variable, so the T distribution is also quite variable. As n gets bigger, S gets more and more accurate, more like this actual standard deviation of the population. And because of that, it becomes more and more normal.